Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 5, Section 2, Chapter 4, Topic 3. Control charts are indispensable tools in semiconductor packaging manufacturing for monitoring and analyzing process performance. They provide a visual representation of process variation over time, allowing operators to detect trends, patterns, and anomalies that may indicate potential issues or deviations from target values. By establishing control limits based on historical data and statistical analysis, control charts enable proactive quality management and process improvement, ultimately leading to enhanced product quality, reliability, and efficiency. A. Shewhart in the 1920s, control charts serve as a fundamental component of statistical process control, SPC, providing a systematic approach to quality management and improvement. Purpose and benefits of control charts. Control charts serve several key purposes in semiconductor packaging manufacturing, including A. Monitoring process performance. Control charts enable operators to monitor process parameters, such as temperature, pressure, flow rates, and defect rates, in real time, allowing for early detection of deviations or abnormalities. B. Detecting special causes. Control charts help distinguish between common cause variation, inherent to the process, and special cause variation, resulting from external factors or anomalies, enabling operators to identify and address root causes of process issues. C. Establishing control limits. Control charts define upper and lower control limits based on historical process data, providing reference boundaries within which the process is considered stable and predictable. D. Facilitating continuous improvement. By visualizing process variation and trends, control charts support data-driven decision-making, process optimization, and continuous improvement initiatives, leading to enhanced product quality and efficiency. Types of control charts. There are several types of control charts commonly used in semiconductor packaging manufacturing, including A. X-bar and R charts. X-bar and R charts monitor the central tendency, mean, and dispersion range of process data, respectively, making them suitable for variables data such as dimensions, weights, or temperatures. B. Individuals and moving range (I-MR) charts. I-MR charts track individual data points and their moving ranges over time, providing insights into process stability and variability for small sample sizes or discrete data. Circa P charts. P charts, or proportion charts, monitor the proportion of defective items or occurrences within a sample or subgroup, making them suitable for attribute data such as defect counts or pass-fail outcomes. D. C charts. C charts, or count charts, monitor the number of defects or occurrences per unit or subgroup, providing insights into defect rates and process variability for discrete data. Establishing control limits. Control limits are critical components of control charts, representing the boundaries within which the process is expected to operate under normal conditions. Control limits are typically derived from historical process data using statistical methods such as A. Standard deviation method. Control limits based on standard deviations from the mean, e.g., plus or minus 3 sigma for X-bar and R charts, provide a measure of process variability and identify outliers or extreme values. B. Range method. Control limits for R charts are often derived from the range of data within each subgroup, reflecting the dispersion or spread of process variation. C. Probability distribution method. Control limits can also be calculated based on the underlying probability distribution of the process data, such as the binomial distribution for P charts or Poisson distribution for C charts. Thanks for watching. Please like, share, and subscribe.